Okay, so good morning. I'm Mircea Mihulet from Romanian Meteorological Administration, and I will be presenting a method for enhancing the quantitative precipitation estimation using an ensemble of machine learning models applied on weather radar data. The study was conducted in the frame of the WEMIL project by a joint team from Babeș-Bolyai University and from the Romanian Meteorological Administration. And as the title indicates, the central goal of the research was to investigate if machine learning models could be employed for estimating the quantity of precipitation based on observation made by the weather radar. Quantitative precipitation estimation, or QPE, refers to the process of determining the amount of precipitation, such as rainfall or snowfall, that has occurred over a specific region or a time frame. Traditionally, QP is accomplished by using various sources of data, for example, interpolated rain gauge information and networks of weather radars. Weather radar has a big advantage as it provides a higher spatial and temporal resolution. However, it's important to acknowledge that this method is not without its challenges, as there are several factors that can induce errors into the process, such as radar calibration accuracies, signal attenuation, ground clutter, range limitation, and partial beam filling. Hence is the relevance of the present study that is intended to bring some improvements to this process, especially in the context of operative nowcasting. So why is QP important? QP has a crucial role in protecting lives and the economy. As one of the most pressing concerns associated with heavy rainfall is the risk of devastating flash floods, overflowing rivers, landslides. And according to the World Meteorological Organization, flash floods alone cause more than 5,000 fatalities annually. This figure highlights the need for accurately estimate and quantify precipitation, as it directly impacts our ability to predict and respond to these severe weather events. A precise QP provides valuable insights into the intensity and distribution of rainfall across a specific area, and this information serves as a vital tool for emergency management, enabling also timely warnings, evacuation measures, allocation of resources effectively. In order to illustrate the importance of QP, in the following slides, I will present a situation from last week from the central region of Romania. On the 3rd of June, on Saturday, it was a day of strong convection that resulted in heavy rainfall that further resulted in flash floods, as you can see in the images on the right. You can see on the radar images that we had accumulations of more than 80-90 liters per square meter. So several orange and red weather warnings have been issued, as the risk for flash floods is greater, especially in these mountain areas, as you can see also here on the right. The weather warnings have been issued using mainly the radar data, in particular the 1-hour precipitation product, the one that is depicted here in the image on the left. This 1-hour precipitation, or OHP, is a derived radar product of our weather radar that estimates the 1-hour precipitation accumulation on a 1 degree by 2 kilometer grid. This product ranges from 0 to around 200 liters per square meter and helps assess the rainfall accumulation for this type of flash flood warnings. Here in this image, also from Saturday, the OHP estimates are lower than in the first case. So here we had around 80-90 liter per square meter, here around 100. Here the estimates were lower, but as it was in a mountain region, also a red code warning has been issued. And you can see that although the flash flood didn't occur exactly when the red warning was issued, it occurred 1 hour later. The flash flood has been forecasted, and the authorities have been warned about this danger. Here also it's a product based on the 1 hour precipitation accumulation, but it's on 24 hours. So you can see that in many areas the entire quantity of precipitation was accumulated in just 1 hour, or maybe even less than 1 hour. And as the rain gauges network has an extent in the range of just several hundred points across the entire country, the importance for weather radars in estimated rainfall is obvious. So here in this mountain region, the number of weather station and rain gauges is limited. In the following slides, I will illustrate several methods for QP estimation used by the Romanian Meteorological Administration. First is the method that I presented before based on weather radar, and here is an estimation for 24 hours from one day in May this year. The second method that I present here is a method that uses data from weather stations on the same day as in the previous slide. And it can be noticed that the spatial coverage of the network is rather limited, as at the moment there are only allowed around 165 such stations, but the network will increase to around 550 in the next 2 years. And as you can see, the data could be presented either as points or as interpolated on the map. Sorry. Complementary to our weather station network, we use data from Hydrology Institute, from stations that measure only rainfall, and as they have a denser network, and it can be noticed that the difference in the spatial distribution and the accumulation values in the interpolated product. So you see there are some differences in the end result. In the end here you can see a comparison between the three products, and a fourth product that is built using data from different sources. And it should be noticed that these products are not generated in real time. So the radar data and information from the stations are the only sources used in nowcasting. And as the weather stations and rain gauges networks have a limited spatial extent, the radar data is the main data source employed in nowcasting in Romania. So our research was intended to answer three research questions. First research question was to what extent the stacked machine learning model does increase the performance of estimating the rainfall rate from the reflectivity data compared to individual machine learning models. The second question was how effective are the machine learning models to make estimation of the 1 hour precipitation using only the reflectivity data from the first elevation levels. And the third question that we wanted to answer was if the stacked models bring a statistically significant performance for the QP with respect to the performance of current operational baseline products. So regarding the first question about the stacked machine learning models, in our study, 6 machine learning based regressors were used for investigating the performance of the QP. It was 4 individual machine learning regressors, deep neural network, a support vector machine, k-nearest neighbors, and random forests, and 2 ensemble regressors obtained by combining the individual learners using stacking learning paradigm. For the DNN, for the deep network neural network regressor, it was used custom architecture, while for the other 3 models, we used their default configurations. Regarding the stacking ensemble, this one is a method used in the ensemble learning, which uses multiple individual machine learning learners for obtaining a better predictive performance. Stacking involves training a machine learning algorithm on the top of the stack to combine the prediction of several individual machine learners. The idea behind the stacking is the following. The base algorithms are trained on the available training data set. Then the algorithm on the top of the stack is trained on the outputs of the base learners in order to make the final prediction. And machine learning literature established that the stacking generally provides better predictive performance than any single trained model. The 2 stacking models we use in our we use 2 stacking models in our study, and the first one is we call the stack PLS with the DNN support vector machine KNN and random forest regressors, and on top of the stack we had a partial least squares predictor, the PLS, and the PLS is a variation of the linear least square regression, where the model reduces the number of variables used for regression. And the PLS is especially useful for cases where the instances have a high number of variables, and there is a high chance that the variables are correlated. And the second stack model that we used, we called the stack DNN. It had the base, the PLS, the KNN, and the RF regressors. And on top of the stack, the customized deep neural network predictor. Regarding the data, regarding the data set used, in our study we used 2 types of meteorological data. That is the weather radar data and the precipitation data from weather station. The radar data was collected using a VSR WSR 98D single polarized Doppler weather radar, the one in the picture here, that is located in the central region of Romania. The radar allows us to gather information about clouds on a radius covering over 200 kilometers. As you can see, the range is actually affected by this range is affected by a mountain range lying around this region, around Transylvania, and the mountain range is about 100 kilometers from the radar, but we compensate this loss by using data from radars outside the mountain range. The VSR radar employs a scanning strategy known as VCP21, which involves a complete scan every 6 minutes. And this scanning includes 9 elevation levels starting from 0.5 degrees and increasing by 1 degree for the first 4 elevation angles. For our experiments, we focused on analyzing the reflectivity data from the first 2 elevation angles and on the OHP, on the 1-hour precipitation data. And the data was collected during 30 non-consecutive days between May and July 2016 to 2021. The second type of meteorological data that we employed is represented by the 1-hour rainfall, collected by rain gauges from 40 weather stations of the Romanian Meteorological Administration, all located within around 180 kilometers from the weather radar. The observations from this network are transmitted to a central database every 10 minutes, hourly, and whenever reaching a certain threshold. And the image depicts the geographical distribution of the weather stations used in this study, and one of the rain gauges is located in the same location with the weather radar. So the goal of the machine learning model was to estimate the accumulated rainfall using radar data as input. Radar data in this case being the reflectivity at the two lowest elevation angles. In order to create the data set to be used by the machine learning models based on reflectivity, rainfall as input output, it was necessary to create correct reflectivity rainfall pairs. The first step, since we only had the rainfall data for specific locations, was to find the correct reflectivity data for the location of each of the weather stations. For reflectivity data for each timestamp, we had data grid that gives the data for the reflectivity in the area around the radar. And each point in the data grid represents the reflectivity value at a certain geographical location. For the rainfall data, there is one value for each weather station for each timestamp ideally, but in reality there are often missing values. Thus, in order to pair the rainfall value with the correct reflectivity values, the problem was reduced to finding the correct coordinates for each weather station on the radar's grid map. From a meteorological point of view, the rainfall rate in a certain location at a time step t may be influenced by the values for the reflectivity at previous time steps, for example, t-1 to t-2, 3. Not only that particular point, but also in a neighborhood of that point. Thus, we consider a neighborhood of diameter d around the central point. From a machine learning perspective, the intuition behind this decision was that using data from around the station and not just the value above the station is that multiple data characteristics would give the machine learning models more informative data from which they could learn to extract only the relevant features which are correlated with the rainfall rate. And from a meteorological point of view, the data from around the station would help to mitigate the effects, for example, of storm tilt or under the beam phenomena. Data was collected from 40 ground weather stations over 30 days, 24 hours a day. Thus, we had around 29,000 instances for the study. 60% of the instances were used for training the models, 10% for validation, and 30% for testing. As I said, the rainfall rate in a particular location at a certain time moment might be influenced by the conditions in the neighborhood of the previous time steps. So for the neighborhood of diameter d, we used three values, 3, 5, and 7 numbers of cells. And these dimensions of the relevant neighborhood were selected based on a minimum, average, and maximum convective cell propagation speed, which has an average value between 50 and 40 kilometers an hour. as the geographical distance between two neighboring values is around 900 meters. For our experiments, we chose values for diameter d corresponding to distances between 9 kilometers and 4 kilometers, which are correlated with the above mentioned propagation speeds. In this image, we represent the rainfall data, which is illustrated, which illustrates 1 hour rainfall recorded at the weather station. The horizontal axis depicts the rainfall in millimeters, and the vertical axis shows the number of instances labeled with a certain rainfall rate on a logarithmic scale. Thus, the histogram shows the number of instances for which the ground truth was in an interval represented by each bucket. You can see that the instances with ground truth 0 were depicted in a separate bin in order to highlight the number of such instances. More than 75% of instances were zero liters per square meter. This imbalance is not unexpected. The storms are usually localized, and therefore only some 40% of the weather station will read non-zero values at a time. And while there are large periods of time where with no storms or meteorological events, when all readings will be zero, so it was expected that most values for the 1 hour precipitation would be zero, and higher values will be rare. This, however, raises the difficulty of the regression problem, as machine learning algorithms tend to have a bias towards the majority class, so towards zero in this case, simply because there are more instances to learn from. About the results, this table presents the values for the performance metrics obtained by each of the machine learning models. As previously said, there are three possible values, 3, 5, and 7, which were considered for the diameter of the neighborhood for the data representation. In what concerns the impact of the neighborhood hyperparameter D on the result, we noted that generally there has been a slight performance increase for higher values of D. And regarding the metrics, for most of the metrics which are marked, which are highlighted, the stacked model. The stack model PLS has the best performances. Also from this table, we conclude that the best performing machine learning model in our experiment is the stack model stack PLS. And for this model, there are two values for the hyper diameter, 5 and 7, which provide the highest value, 23. From a meteorological point of view, values 5 and 7 for D represent the neighborhoods up to 1.84 kilometers, relevant for storm propagation speeds between 80 to 40 kilometers an hour, so exactly within the average speed considered for such phenomena. And the hyperparameter D equal to 3, which would be relevant for quasi-stationary storms, which have a lower occurrence, displayed a lower performance in our experiments. So perhaps in the data set that we used for training, we had more moving cells, and perhaps in the case of stationary cells, the performance was not that great. Further, we compared the results with two baseline quantitative precipitation estimation products. One is the 1 hour precipitation, the OHP, and a method for estimating the rainfall rate using the ZR relationship. We know that for our stack PLS regressor, the value 5 for the neighborhood has been chosen as it provided the best results. And here you can see that the best results are also highlighted in the table. In the following slides, you can see a visual comparison between 1 hour estimations provided by our stack PLS regressor and the 1 hour precipitation and ZR baselines. The figures showed that the rainfall estimation for each geographical location around the radar, and 1 pixel in the image represents 1 cell in the grid map. The interpolation method used here is currently in operational service at the Romanian Meteorological Administration, and it's a regression Kriging model that combines ground observation with radar data, precipitation estimates, and local topography. And it is generated the sub-daily precipitation grid data set using this method. From a meteorological point of view, when we compare the results depicting the interpolated weather station data with the estimation from the stack PLS regressor and the OHP, we can see that the stack PLS regressor has outperformed the OHP product that is currently used in operational activities. As a stack PLS regressor better identifies both the area with precipitation and the intensity. You can see that the stack PLS regressor and the OHP are underestimating the values in the northeastern part of the map, which could be because of the distance from the weather radar is around 200 kilometers, which in turn leads to a poor scanning of low altitude levels, where precipitable clouds usually are to be found. Further observation regarding the stack PLS regressor is related to the to the cells in the central part of the map, the noise here, which are due to the ground clutter caused by the hilly terrain. But this type of error is usually easily identified by the meteorologist, given its unnatural aspect. Regarding the method, the ZR method, based on these images, we can see that the ZR method seems to be making to make the best estimate related to the ground truth interpolated map. But this is probably because this method, the interpolation method used here, employs beside the weather station data also radar reflectivity, which in this case brings the estimation closer to the ZR method. In the last slide here, we present the maximum reflectivity for the entire interval. And we can say that the computational results are highlighting that the ensemble learning models are more effective compared to the individual learners, and also bring a statistically significant improvement compared to the OHP and ZR baselines. And furthermore, our experimental findings reported that the hypothesis that machine learning models are effective models for making estimation of the 1-hour precipitation using the reflectivity data on the first two elevations. And in addition, the ensemble learning regressor stack PLS increased the performance of estimating the rainfall rate compared to the individual machine learning regressors. Thank you, and if you have any questions,